Hi, everyone. My name is Kennedy Sleet, and today I will be talking about what I did this summer and my specific research. I'm currently a student at the University of Arizona. I'm a rising senior. And yeah, the title of my project is The Cosmic Infrared Background Deconstructed. So before we get started, tying back to my title, the cosmic background deconstructed can really be used to kind of untie cosmic mysteries with the use of galaxies and the CIB. So what is the CIB? The CIB stands for the cosmic infrared background, and it's basically infrared radiation that comes from stellar dust. So actually looking at the CIB, you can, like I said, expose the cosmic mysteries. And specifically, what I focused on was exposing the history of star formation. So, to actually disentangle the CIB itself is very difficult. There's a specific technique that we did have to use, and that technique is using the amplitude of angular correlation between the galaxies and the CIB with narrow range of redshifts. And the reason as to why we can do this is because because the galaxies with a narrow range of redshifts are actually proportional to the CIB at the specific range. So the galaxies that we use come from the BOSS survey, and the BOSS stands for the Baryon catalog, and we're basically using it as a function of mass and redshift. So the mass that we're looking at, or the specific galaxy's mass, ranges from about 2 times 10 to the 13th power, or the solar mass. So that's very big. And I'll talk about a little bit more about the redshift in the future slides. So basically interpreting the measurements in terms of physical parameters. So taking the data, at the end, what the main goal was to fit this data to the best curve. So up to this point, I built the infrastructure to do this. However, unfortunately, I didn't have enough time to actually fit the data to the perfect curve, but I'll also kind of explain that in a minute. So also a future method is, if time does allow, to actually take these results and compare it to state-of-art simulations that are currently used by the Simons Observatory. Okay, so right here is a couple of images that I use to actually get my final results. So to the bottom left, I don't know if you can see my cursor, but this is the mole-wide view, or the halo view, of the fluctuations around the mean CIB intensity. To the top is the mask that actually is used to map out the galaxy distribution. So this map is not the actual map that we use for our results, but this is the mask of that map. So right here is the power spectrum. A little information about the power spectrum. The power spectrum is actually, or cross correlation is actually essential, because you're basically taking the measurement that traces the specific movements of 2 or more sets and using that relative to one another. So the power spectrum is actually used a lot in astrophysics studies. For example, the CMB, which is the cosmic microwave background, a lot of people that study that use the power spectrum to figure out different things. For example, one project is like reionizing the matter from like the early universe, early stars, and the early black holes. You could also use it to kind of, I guess, look at the scattering of hot gas. So here's the final result of or not the final, but this is an example of the cross correlation of the power spectrum. Also, we did compare this to literature itself, and it matches, so that's great as well. So specifically, the galaxies that I use to look at comes from the BOSS survey, which stands for the Baryon Oscillation Spectroscopic Survey, and then the actual CIB map, which is right here to the bottom left. And basically cross-correlating these two, you can expose the history of star formation. And the reason why you can do this is because when the star formation rate actually increases, the amplitude of the signal increases as well. So overall, the statistical data, is the measurements are very high, so that's really good. And fitting the theory curve to the data will help actually look at this data and connect it to things that we have questions about. What was going on in the beginning of the universe? How can you extract this information and connect it to literature itself? So right here is my main results. This is the bind cross correlation with error bars. And you don't actually necessarily have to bind the statistics, but the reason why we did is it just reduces the noise. It's easier to interpret the data as well when this information is bind. So to the left, or sorry, the y-axis, you can see the actual cross correlation. And on the bottom is L, which is in terms of theta. So it is inversely actually proportional to theta. So as theta increases, L decreases. That's how you can kind of read the map. Let's see. So overall, I did want to talk a little bit more about actually curving or finding the best fit for the data. So this example is an example of what the best fit would look like. This data is not the actual data. This is the data, but as you can see, it's very similar. So basically using different functions, for example, this is the power law function, but by using different functions, you can actually find the best fit for this data, which is what I plan to do in the future. So yeah, the signal that we use to measure is proportional to the star formation rate. And basically, just to give more information about this redshift, this is ranging from about 0.4 to 0.7. So that's light that was traveled about from 5 billion years ago, which is amazing. Overall, I think the coolest part about this project was not only are you looking at the CIB, but you can actually connect it to what happened in the early universe from billions of years ago. So in the future, we can actually divide this redshift range into smaller ranges, which will give you more accurate data and also fitting the theory curve as well. So yeah, fitting the theory curve to the best fit is a future goal, and also to isolate the galaxy kind of just information that you don't really need to look at the star formation to isolate those properties. So here's the references from my project. And overall, I would like to thank the Simons Foundation, the Flatiron Institute, my mentors, Simone, Antone, and Noah, and of course, Casey, Shannon, and Seren for setting everything out. It's been amazing. I guess I talked really fast. I'm sorry about that, but thank you. Any questions?
Great, thank you. Any questions for Kennedy? So I had a question. You had the one plot where you had some data. You said it wasn't the real data, but it was simulated or something, and you had a curve. Yeah. So it looks like to me, the best fit model, why is it that it kind of goes to 0? Because if I were to kind of take that fit away and I looked at this data, it just looks like maybe something that starts at 8 and kind of decreases might be a better fit. So could you just say why you chose a model that looks like that?
Sure. So actually, I do plan on using a lot of different models. This was just the one that I decided to do first, which is the power law function. As you can see, what's really important about looking at this is it doesn't fit perfectly. So being able to look at, what model doesn't fit that right can help essentially lead to different functions that you can use. So yeah, this isn't the best fit model technically, but it is just an example of a model.
Great, thank you. Are there any questions from anybody on Zoom? Okay, let's thank Kennedy one more time.